In question letter D, they're going to give us the recursive definition, which officially is both of these parts combined, and they're going to ask us what each of those individual parts means. So when you see the phrase recursive definition, definitely get used to the idea that it's a two-part expression, kind of like we saw on the previous page. You'll see down below in question number 5, these are more examples of recursive definitions. Letter A has two parts, letter B has two parts, letter C has two parts. So that's kind of normal. To see a recursive definition, you're going to see two parts. Each part has its own significance, so I want to make sure that we understand the significance of each part so that we can see how these recursive definitions can be helpful to us in future problems. The first part of the recursive definition says t of 0 equals negative 8. That is just a specific term in the sequence. So notice where it says, what does this mean? I'm just going to try to write it out and say it at the same time. This is a specific term in the sequence. Now, to be particular, this is the 0th term in the sequence. But they could actually give us any term in the sequence. They could say t of 1 equals, t of 2 equals, t of 10 equals. They could give us whatever term they want to. So the first part of a recursive definition just gives us a specific term in the sequence. It's kind of like telling us where to start. This is saying, hey, start thinking about this sequence at negative 8. The second part to the recursive definition says how to get the rest of the terms. After you call out one specific term, how would you get the next one and the next one and the next one? And that's what this second piece is trying to say in very mathy language. If you translate this expression, what it means is to get to the next term in the sequence, take the current term and add 6. That's kind of a direct translation of these parts. T of n plus 1 is like saying the next term. T of n is like saying take where you currently are. And then the plus 6 is obviously saying add 6. So if you're not really sure what that means, let's look at the table and see if it makes sense. Like, let's say I'm currently at the 3rd term. This definition is saying to get to the next term, that would be 4, take the current term and add 6. And we know that's true. To get to the 4th term in the table, I had to take my current term of 10 and add 6 to it. And to get to the next term, notice to get to the next term, I take the current one and add 6 to it. And then to get to the next term, I take the current one and add 6 to it. So notice how this definition would work for even like the next term after this. Let's say I'm currently at 8. If I'm currently at 8, you can think of this almost like a formula. If I'm currently at 8, let's assume n equals 8. That's the term that I'm currently at, and I want to get the next one. To get to the next one, we would say t of 8 plus 1 equals t of 8 plus 6. Notice how I just plugged in the 8 into my formula? The inside of this parentheses, 8 plus 1, is really 9. And 9 is really the next term in the sequence. So when I look back, I would say, oh yeah, if I'm at the 8th term currently, and I want to get to the 9th term, that would be the next one. So my translation seems to make sense. And it says t of 9 equals t of 8 plus 6. And I would think logically, and I'd say to myself, oh, t of 8, that's the 8th term. Well, according to my table, the 8th term is 40. So 40 plus 6 is 46. And sure enough, if I was looking at my table and wanted to get the next term, I'd take the current one, 40. I'd add 6 to it, and voila. There's the 9th term, is 46, just like the formula predicted. So the formula is a way of predicting what comes next in the sequence. Obviously, the table is an easy way of predicting that as well. So the formula and the table kind of say the same thing. They're just two sides of the same coin. And in general, if I was to translate this, I would translate the expression exactly how we said it. That to get to the next term, we would take the current term and add 6. Well, this just means it's a way to generate the next term. So in general, a recursive definition is a way of basically giving you somewhere to start and giving you a code for how to generate what comes next. In fact, the recursive definition is almost kind of like coding. So if you've ever been interested in coding or computer science or any sort of computer programming, even if you've taken engineering type classes where you do some sort of coding to, say, for example, control the behavior of a robot or something, that coding is usually done in some sort of recursive way. So recursive definitions actually have lots of implications in the world of coding and programming and computers. And if that is an area that interests you, this might be a particularly good lesson to make sure that you think about, because many of the things that we do in coding involve programming just this way. You tell a computer where to start, and then you tell it what to do for each subsequent step. That's usually what coding is. It kind of tells you what to start doing, and then it tells you each next step based on wherever you started. So that's what a recursive definition is doing here. It told us where to start in the table. It told us start at the 0 term of -8, and then it told us to get to all the other terms, just keep adding 6. So that general code for what to do is the recursive definition. Once you understand what a recursive definition is, we'll try to make a little bit more sense of it in question number 4.